Or to the cloud. All right, I think I'm doing it. Yeah. All right, so we did rate laws the first lecture. Second one we did how does concentration depend on time for first order only. Last time we did something I call collision theory. Well, I'm the only one who calls it that. Everyone calls it that. Today, and so last time was all about activation energy and things like that. And today it's actually another adventure still. It's about reaction mechanisms. So I'm going to talk to you about why reactions have the rate laws that they have and how can you tell what those rate laws are. All right, so let me go ahead and share. Hold on. Okay. All right. Okay. So we've done a lot on reaction rates. I sort of just gave you the rundown of what we've done. But there's like a big question that remains. All right, so we know what rate laws are. Let me get the pen to work here. So today we're going to do reaction mechanisms. I guess that's what it's called. And we know how to find the rate law for a reaction. I was just going over that with one student this morning, just before class, not this morning. It seems like morning, but actually my time is all screwed up because of the 1 hour time change. I actually went to bed at like 1:30 last night. Don't ask me. That always happens when we get the time change. I go to bed really late the first night. But anyway, so we know how to find the rate law, but what we don't know, yeah, I know everybody has it. What we don't know is how to figure out why a rate law is the rate law for that particular reaction. So the big question is, why are some reactions first order and others are second order and others are third order? What determines the order of a reaction? So that's what we're working on today. What determines the order of a reaction? Okay. And so why are some first, second, third, whatever? What determines that? So, and can we tell just by looking at the equation for a reaction what the order is? And you know, we know the answer to this question because if we could just look at the reaction and say, oh, I know the order of that reaction, and we wouldn't have to do experiments to figure out what the order is. So I guess I would say not exactly here. But you're going to see that what I'm talking about next is that sometimes you can, and under certain conditions you can. All right. So let me sort of go logically through something. Okay. So what if a chemical reaction happens in just one step? This reactant, A, just sits there and turns into something else in one chemical event. Okay, it just turns into a products. You could say it just decomposes. It just sits there and it just happens like this. That this is the way it happens. A turns into something, that something is the product. Okay, if it happens like that, shouldn't the reaction rate be proportional to the concentration of A? Of course it should. If that is what happens, yes, then the reaction rate should be proportional to A. So if A just sits there and in one sort of chemical event turns into the product. It just sits. So in other words, if this reaction happens as written, so there's not a whole bunch of steps in the background. It happens as A turns into products. If A just sits there and in one chemical event turns into products, then the more A you have there, the more of those molecules you have there, the more of those molecules will have the needed energy to go over the barrier, right? Because the fraction of molecules that have that energy will be the same because the activation energy is the same. But if there's more of them, you will have more that have the ability to go over the barrier. So the reasoning here, so if A just sits there and in one chemical event turns into the product, let me finish this sentence, then yes, the reaction should be first order in A. That's the only thing there. If A just sits there. So I guess I had asked the question, shouldn't this be first order in A? Shouldn't it depend on the concentration of A alone? Okay, and then the answer is, if it just sits there, turns into something else, then yes, the rate should be proportional to the concentration of A. And like I said, the reasoning is, if more A is present, then a greater number of A molecules will have the needed activation energy. Remember, this fraction, this thing is the fraction of, in this case, because there's no collision, it would just be the fraction of molecules with the required activation energy. If you take a fraction and multiply it by a small number, that's a small number of particles that can get over the barrier. But if you have more A, you take that fraction, you multiply by a larger number, you'll have more that go over the barrier. The reaction will be faster. So if more A is present, a greater number of them will have the needed activation energy, and this is the reason why, and the rate will be faster. And in fact, the rate will be proportional to the concentration of A to the 1 power, if this is the way the reaction happens, as written. Okay, now, what about if you have a simple, so suppose instead the reaction happens like this, where you have A plus B goes to products. Okay, if that's what happens, and that's the way it happens, it is a single chemical event where A collides with B, and the complexes, that the collisions that have enough energy to go over the barrier go over. If a collision with A and B is all that happens, so if this reaction occurs as written, then it makes sense that the rate will be proportional to the concentration of A and the concentration of B. Because if you increase the concentration of A, you increase the number of collisions because it's more chance of collisions. You also increasing the number of collisions that will have the required activation energy just by increasing the number. And so it would be proportional to the concentration of A. And the same would be true for B. So it's really the same reasoning. More A means greater number of collisions with B. Also, more collisions will have the needed EA. Not because the activation energy has changed, but just because you're multiplying that fraction, that's what this is, by a larger number. So you have more collisions that will have the needed activation energy. And so the rate law for the reaction, as long as it occurs as written, will be K, A, B. Okay. All right. So I don't know. Am I getting through? Does this make sense to anybody? How is it going? Do you believe me? Do you think I'm lying to you? No comment? Do I have any chats? No chats? Yeah, makes sense. All right. Okay. So, so if that's the case, you know, why can't we just look at a reaction and know its rate law? Think about that for a minute. Okay. And the reason for that is because most of the time, very often in chemical reactions, they don't occur as written. They don't occur. Like you see a reaction, that is the overall reaction. That is not showing you the actual steps that happen, the sequence of steps that happen in order to get the reactants to go to those products. You're not seeing that. You're only seeing the overall reaction. So why can't we just look at a reaction and know the rate law? And the answer to that is because most reactions occur in steps. And the overall reaction does not show you those steps. So you don't know what single molecular events are happening. You only see the overall picture, okay? So what has to happen in order to figure out a rate law? Well, what has to happen, well, first of all, you could figure out the rate law experimentally, but in order to understand why that's the rate law, so to understand why a reaction has a certain rate law, you know, we've done the experiment, let's say, to figure out the rate law. We know what it is, but why? Then you have to really think about what is happening in that reaction. And you have to come up with a series of steps that goes along with the experimental rate law. So I know this is kind of complicated. So I'm going to give you a very simple example. Okay. And I want to tell you that when finding these steps of a chemical reaction, this is one of the most beautiful things in chemistry. And by the way, if you like this kind of thing, you'll love organic chemistry, because organic chemistry is all about what is actually happening when you have an organic chemistry reaction. And it's all about elucidating the mechanism. So this series of steps, finding the steps of a chemical reaction, is called finding the mechanism. So the mechanism is just the series of steps in a chemical reaction. So I told you I was going to give you an example, and I'm going to give you a very simple example from organic chemistry. I actually remember it. I took organic chemistry last in 1977. So anyway, here's a reaction. We have a methyl group. Well, I'm going to write it as CH3, just why not? It's actually the carbon, of course, that's attached to this carbon. And then I have a CH3 here and another CH3. And here I have a bromine. Okay. And so this is actually, you know, a simple molecule with 3 methyl groups and a bromine on a central carbon. And it combines with chloride ion. Okay. And it produces, well, what happens basically is that these guys change places, and you end up with the chlorine over there and a bromide ion instead of a chloride ion. So basically, you could see there's a few things are going to have to happen here, but the sequence of how it actually happens, so how this actually occurs, is the mechanism. Okay, so I have that on this slide here. Same thing, I just repeated it. All right. This compound, I'll call it C4H9Br because that's what it is. Okay. And here it's C4H9Cl. Okay. So it's a reaction between the C4H9 bromine and the chloride ion. Like I said, it's about the simplest reaction from organic chemistry that you can have. And a Cl replaces the Br here. Okay. So let me ask you something. Well, let me first say, oh yes, the bond between the carbon and the bromine, this bond here is going to have to break, okay? And this bond here is going to have to form. But how that happens, there's a few different ways it could happen, but I'm going to, okay, so if the reaction occurred as written, in other words, if it happens exactly as how I have written it here, if it happens from a collision of this molecule with this ion, leading immediately to the formation of this compound and this ion, so if it happens just like that, what would the rate law be? So remember I said if a reaction occurs as written, okay, and I did the A plus B example. Let me show you. Let me go back here. Okay, if this reaction here, A plus B goes to products, if this happens as written, okay, A plus B goes to products, then it's first order in A and it's going to be first order in B. Okay. So now we have this is really the same type of reaction. The C4H9Br, that would be A, the Cl minus would be B. If it happens as a simple collision between these two, resulting in the products that are written here, what would the rate law be? Somebody turn on their mic and actually tell me what the rate law would be. So rate would equal what? If it occurs as written, it would be what? First order in, come on, help me out here, somebody.
Is it first order in A and first order in B?
Yeah, but of course, A and B are not what these molecules are called. So we put in the right,
Oh, sorry.
Yeah, that's fine. Perfect. Yes, that's what the rate law would be. If this reaction occurs as written, if the reaction occurred as it's written here, this would be the rate law. Okay, so now I'm going to show you what the rate law actually is. So if it occurred as a collision, like we said, then it should be first order in each, as we have written here. But, however, its rate law is actually found experimentally to be this. First order in C4H9Br. Okay, so obviously, well, obviously to me, because I've been doing this a long time, but clearly, if this is the rate law, this reaction cannot happen like this, like it's written here. Because if it did, this would be the rate law, and it's not. Okay, so it's found experimentally to be K times just the concentration of that one reactant, not the chloride, but just the C4H9Br. So this reaction does not occur as written. If it did, the rate law would reflect that. And it would be rate equals K C4H9 Br Cl minus, but it's not. Okay, so what is really happening? In fact, this reaction happens in 2 steps. The sequence of steps, like I said, is called the mechanism. It has a 2-step mechanism. Okay, now I'm going to show you a slide that shows you that mechanism. Okay. All right, so it's 2-step. This is the first step right here. Electrons from this bond, there's 2 electrons in that bond, right? The 2 electrons go over to the bromine. So when that bromine picks up those 2 electrons, it becomes a bromide ion. And there's the 2 electrons there that it picked up, okay? So the 2 electrons from the bond move over to the bromine. What happens? What does it leave behind when it does that? So now you notice the carbon here has only 3 bonds. Okay, C has 3 bonds. So what is the formal charge on that carbon? Remember, to calculate a formal charge, you divide each bond in half. And 1 electron goes to each atom. So this carbon in the middle only gets 3 electrons. So the carbon in middle has 3 electrons, but it had 4 valence electrons. So it has 1 less. So what does that make the formal charge on this carbon? Makes it plus. Okay, so the formal charge is +1. Now, this is probably definitely, unless you learned it somewhere else, this is the first time that we've seen any molecule with a carbon where the carbon has a charge. It's actually very unusual to have a compound where a carbon is holding a positive charge. It's pretty unstable, and it has a name. We call it a carbocation. Okay, but anyway, it's pretty unstable. So you know that you're going to have to go up in energy to get over that barrier. All right. So it says, so you form this carbocation. It's what we call a reaction intermediate. And the reason I know it's an intermediate is because when I go to the next step, here's the next step. In the next step, the 2 electrons from the chloride ion go to form a bond here between the carbon and the chlorine. And you could see this guy has a negative charge and this guy has a positive charge. There is a very strong attraction between the plus and minus charges. That's going to make this reaction happen very readily. So while this reaction, the first one, happens very slowly because this is unstable, okay, this second reaction happens very fast. And you could see that the bond does indeed form between the C and the Cl, and we end up with the products. But this first step is just this molecule doing something, okay? So I can actually show you what the reaction profile of this molecule looks like. And the first step is very slow. When something is very slow, what do you know about the activation energy? If a reaction is slow, what must be true?
Low activation energy.
A low activation energy means that a lot of molecules will have the energy to go over it, and the reaction will be fast. Okay, so
So it's the
maybe you
opposite.
meant it would happen in a small time, because when we were in lab, for example, we were measuring time, and it would happen in a short time, but that, oh, sorry, it would happen in a long, wait a minute. Yeah, it would happen in a long time, but and it would be a small rate. So this reaction is slow, and the activation energy is large. So in other words, very few molecules will have the energy to go over it. So a lot of those collisions will be unsuccessful. They will go right back where they started from. Okay, just a small fraction of collisions, this e to the minus EA over RT. Remember, that is in this Arrhenius equation. Okay, this term here is the fraction of collisions with the needed activation energy. The smaller this fraction is, the slower the rate and the longer the time, of course. And as the activation energy goes up, that fraction gets smaller and smaller because you have fewer molecules that can go over the barrier. So if you think about this reaction here and these two steps, the first step, this is very slow. So this has a higher activation energy. This guy here, which is very fast, is going to have a lower activation energy. So I can actually draw a reaction profile, or at least, I don't know what any of these energies are. I do know that this reaction is an exothermic reaction. You wouldn't know that, you'd have to be given that. So that means that here's your reactants, and your products will be lower down in energy. Okay. But what I know is that that first step has a bigger activation energy than the second step. Let me go over this with you. So here is the activation energy. I'm going to call it EA1. Okay. This little sort of valley here, that's the carbocation. Oh, I didn't draw a very good diagram. Let me do a little better. I lied. Sorry. Yeah, I'd rather draw it like that, because the carbocation is itself much less stable. So that positive charge, that's what this thing is. That's this whole thing here. So in the first step, it forms that carbocation, which is itself less stable than the reactants or the products. You can see it's higher in energy. So a lot of times when you form something and then it reacts away, well, first of all, what we call that thing is we call it a reaction intermediate. We give it the symbol I. So when you see a diagram like this, where you have an activation energy for the first step, and then this little thing here, that would be the activation energy for the second step. Okay. The intermediate is like in that little valley in between the two peaks. We have a transition state here. That's what that symbol means. And then we get to that carbocation, which is more stable than the transition state, but less stable than the reactants and the products. And then we have a teeny little activation energy for the second step. And the reason I know it's small is because this is fast. So it has a lower activation energy. And finally, we go down to the products. Okay. So we form a reaction intermediate in this little valley, And then it's much easier to go from there to products because you don't need to have as much energy as for the first one, because the activation energy EA1 is greater than EA2. So that means the first step is the slow step. The second step is fast. Does anyone want to ask me a question about this? Because I bet that some of you have questions. And if you're thinking of asking one, but you don't know if you should, try to do it for the other folks in the class, because other people may have questions as well. So Erica, Morgan, anybody, Julia, Jacob, Daisy, have a question about this? Can't formulate it, or is it okay?
I'm not sure how to ask.
Well, what are you thinking about?
I'm not really sure how the K is the.
Anybody help her? Or are intermediates common? They are very common. Absolutely. They're all over the place. Yep. Yeah. I wouldn't call them intermediate reactions. Intermediates are like, they're like interim products. They're like products that form, that react away. So intermediates don't hang around. So remember I told you that this carbocation is not particularly stable. You could see its energy right here. And it's less stable than the reactants or the products. So a lot of times, species, chemical species, we call them, species can be very short-lived if they're unstable. They'll form and then they'll react to form something else. Okay, so that chemical intermediates come and go. All right, let me show you a more beautiful picture of this. This is just from book, but it works for that reaction. Here we have the transition state. In truth, there are actually two transition states, and it's what's labeled here, but the real transition state is the higher energy one, and that's the important one, because that's got a much higher activation energy here than this one. So it's going to be harder to go over that first barrier by far than to go over the second. So you could think of this diagram as being for the reaction that I just talked about, and forming the carbocation, which will be right here, the intermediate, that carbocation, has a greater activation energy, EA1, than EA2. So step one has a greater activation energy. And when you have a two-step reaction where the first step is slower, then you will see that the first bump goes higher up. And that now you're going from this intermediate here to the next bump, it's much smaller. So this is characteristic of a two-step mechanism, where step one is the slow step, and step two is a fast by, elimination there. Okay. Questions? No questions? Well, listen, if you have a question, why don't you just, oh, is someone in the waiting room? I don't see anyone in the waiting room. Wait. Oh, I don't think anyone is. Okay. All right. So, so we have this reaction, this C4H9Br plus Cl minus goes to C4H9Cl plus Br minus. And we say that, and we know from experiments that it's first order in C4H9Br, and it doesn't depend, it's 0th order in Cl minus, so that the rate law is K C4H9Br. So you will notice that there is no chlorine at all in this rate law. Cl minus does not appear in the rate law expression at all. So why is that? I mean, it's still part of the reaction. But if you look at this reaction and the way it occurs in these two steps, it's clear that only the slow step is involved in the rate law. So the slow step actually determines the entire rate of the whole reaction. And it's a very important thing to realize here. So the slow step, or I should say the slow step's rate determines the rate of the entire reaction. And since the slow step is just C4H9Br turning into that carbocation, then that's the only thing that's going to be in the rate law. So the slow step's rate determines the rate of the whole reaction. So since the slow step only involves the C4H9Br reactant, then the reaction rate is determined only by that concentration. Okay. And I know I spelled determine wrong, but I'm leaving it. So this means that if you have a reaction that occurs in, say, 10 steps, that the rate law for that reaction will be the rate law for the slow step. So, you know, that means we really simplified things a lot. We don't have to worry about the other 9 steps as long as they're faster than the slow step. So I'm going to write that down because I think that's really important. So suppose you have a 10-step mechanism, and there are 10-step mechanisms out there. You know, there's some very complicated chemistry that goes on in this, you know, galaxy. Okay, so suppose you have a 10-step mechanism. Sounds like a 10-step program, but that's not what I mean. That's 12 steps, right? So suppose you have a 10-step mechanism. The slow step determines the rate. So the rate law for the whole reaction, the whole 10 steps, is just the rate law for the slow step. So in a way, this is great because we don't have to worry about the rate laws for all of the steps. We only really have to worry about the rate law for the slow step. And I actually have a great analogy for you. Where is it? Oh, so first let me tell you this. Why is this reaction first order in C4H9Br and doesn't depend on the concentration of chloride? I already told you this. The reason is because the slow step determines the rate and determines the rate law. And the slow step simply involves this molecule. It does not involve the chlorine. So it's first order in C4H9Br and does not depend on the chloride. So this idea of having a many-step process where the slowest of those steps determines how fast that whole thing happens You know, we see this all the time in real life, and we have a word for it. Have you ever heard of the word a bottleneck? You know, if you have a pipe, supposing you have a big pipe, right? But you know, it's got some buildup on the inside, let's say, so let's say we have this big pipe, but we have buildup over here. Okay, and then maybe we have some buildup over here. So the pipe gets very narrow here. Here it's not as narrow. Then it gets even, you know, really here it's really something built up on the pipe. Okay. I remember when all the pipes in my ancient house were changed, and I got to look at some of the pipes from the upstairs bathroom, and man, you could barely put a pin through that pipe. So here it's almost like you have a pipe that's gotten narrow, right? And here it's gotten really narrow. So what determines how fast the water can get through the pipe? It's certainly not this width that's going to determine it. It's this width, you know. So the rate determining part of this pipe is the part that's the narrowest, right? So the narrowest part of the pipe determines the flow rate. So this is like the rate determining part. So it shouldn't be a shock that the rate determining step in a reaction is totally responsible for the rate, the slow step. Here's another instance. So when you go to Boston, to Logan Airport, you know, back when, well, I think traffic is picking up again, but I mean, you look at, you know, Google Maps or something like that. And so I guess I want to say, what part of this map scares you the most? You know, you have to catch a plane on time. Where you don't want to. Yeah, the red part, of course, right? And so you know that you could be going all nice and everything here and nice here, but if that's really bright red, you could sit there for 3 hours, you know, if it's an overturned semi truck or something. So what scares you the most, of course, is the red part, right? That's the rate determining part of this map. Well, chemical reactions are sort of similar. You know, whatever the step is that has the greatest activation energy and is itself the slowest step will determine the rate of the overall reaction. With the greatest activation energy will determine the rate of the overall reaction. Okay. All right. So to know the rate law, you have to know the steps. And you have to know which of them is the slowest. In a mechanism, like I said, the overall reaction is broken down into steps. So what a mechanism is the simple steps that occur in a reaction. But I mean something very specific about the simple steps. These are single chemical events, like a collision between two molecules, or one molecule just turning into a carbocation or something like that, okay? Single chemical events. These simple steps that are single chemical events, we call these elementary steps. They are elementary because they are single chemical events. And when you write down an elementary step, because it actually happens that way, the rate law is obvious. If it involves just one molecule, it's first order in that compound. If it involves a collision of two, it will be first order with respect to each. Okay, so the simple steps that occur in a reaction, these single chemical events, these elementary steps, okay, these occur as written. So their rate laws are obvious. I'm going to show you what they are. Okay. So here's a slide that goes over just what I just said. The actual chemical steps that occur in a chemical reaction is the mechanism. The sum of these steps, I didn't say this, but this is true. If you add up all these steps, that's the overall reaction. Okay, I'll show you about that. Like I said, these are elementary steps. Each is a single, simple chemical event. They can't be broken down into simpler steps, and they occur as written. So here are some elementary steps. These are some of the different possibilities. So if you have a first order situation, like, well, you have A goes to products, okay? That was like what we talked about with the C4H9Br, just forming that carbocation. The carbocation would be among the products of that step. So this isn't the products of the reaction, it's the products of that step. Okay, for each of these until you get to the end one when it, you know, it's, all right, the products. Oh, I'm sorry, these are all right, these are elementary steps. Yeah, maybe I was a little confusing with what I was saying. But if it only involves one molecule, by the way, we say the molecularity is 1. I don't care if you know what molecularity means. The rate for that step, because it only involves A, is proportional to A. It's first order in A. Okay, so if you just have A doing something, it's first order in A, as long as that's an elementary step that cannot be broken down any simpler. If two of the same molecule collide, A plus A, and that gives you products, this is not right. These are the products. This is talking about elementary reactions and products. Yes, it is the product. Sorry. Okay, it's that these are the products of the steps. Yeah, it's just that you don't add these up. These are all separate examples. All right, so for here, you have A colliding with A. So if you have a collision there, that's going to rely on the concentration of A squared. So basically, you look at the reactants in an elementary reaction, and you immediately write the rate law as reflecting that number of each of those reactants. So for example, A plus B, that's going to be first order in A, first order in B. A plus A, that's first order in A and first order in A, which makes it second order in A, actually. Okay, so if you have two of the same, this would also be 2A goes to products. Then you would say, oh, that's second order in A. If you have a collision of 3 A's, that would actually be third order in A. These are all possibilities of elementary steps. Why do you think that these situations are rare? Why does this say rare here? So why would these be rare? So these are the possible things that can happen in steps of a chemical reaction. If you have A plus B, that's telling you that there's a collision between A and B. If you have A plus B plus C, that's telling you that in that step, you have a collision of A, B, and a third hand C at the same time. So now I ask you, why do you think that would be rare? Have these guys, they're all colliding in the soup, in the reaction mixture. What this reaction relies on is a collision of 3 particles at the same time. That's going to be a whole lot less often than a collision between 2 particles. All right, so this guy requires a collision of 3 molecules, A, B, and C, at the same time. because this is telling you exactly how this molecular event occurs. It occurs as written, means that you need a collision of all three. Or here you would need 3 A molecules to come together. Well, molecules that collide with each other all the time, but most of the time it's just 2 molecules. It's rare that you're going to see more than that. That's why these are all rare. So it's very seldom will 3 molecules collide. So those are rare. So if your slow step is just something breaking down, turning into something else like this first reaction here, that means the slow step would be first order. That means the rate of that reaction would be first order. If your slow step involves a collision, say of A and B, then the slow step will have this rate law, and the overall reaction will have that rate law because it's determined by the slow step. So somebody asked, would there be usually more than one reaction occurring with that many reactants? Are you talking about the third order one I just went over? Yeah, if you had 3 reactants, rarely would all 3 collide to form products in one step. You would probably have 2 colliding, forming an intermediate. The intermediate might collide with the other reactant. I'm going to show you some examples of mechanisms that I think will be helpful. So anyway, the point is that the rate law for the overall reaction is equal to the rate law for the slowest step. And I've probably said this 10 times already. So so in the case of the reaction that we studied, this reaction slowly forms C4H9 plus a bromide ion. This is the slow step, followed by C4H9 plus reacting with chloride very fast to produce this. Okay, so this is the slow step, step 1. So the rate law of the overall reaction equals the rate law for the slow step. And since that only involves 1 molecule, that rate will be K, concentration of C4H9Br, will be first order in that reactant. And that will be the rate for the overall reaction as well. And in fact, while I'm here, I can show you, let me try this. So I copy this so I have a little room underneath it. Okay, when you add this up, so the way you find the overall reaction is you can add up the steps. And here's something that forms. This is an intermediate. And then notice that it reacts away. So when you add up these reactions, this guy cancels and it doesn't appear in the overall reaction. So intermediates don't appear in the overall reaction. And the reason why is that they form and then they react away. So you could look at this overall reaction and you really would have no idea that it's first order in C4H9Br unless you know what the steps are. But you could do an experiment and find out that it's first order in C4H9Br. So once you do that experiment and you know that it's first order in C4H9Br, then you know that the slow step has to be the reaction of C4H9Br by itself. So basically, by measuring the rate law, by determining the experimental rate law, it gives you a way of figuring out the mechanism, because you will know what reacts in the slow step. So by knowing, and you do this from experiments, the rate law, you can figure out the mechanism. And that's because the rate law tells you what is happening in the important slow step of the reaction. So if you do the experiment, you find out, oh, this reaction is first order in C4H9Br. Oh, well, that must mean that the slow step is just it doing something. So then you might think, oh, maybe it forms a carbocation. And this is the kind of thinking that gets chemists giddy, because they love this kind of stuff, okay? All right, so I have to just tell you a little bit about the role of a catalyst. And of course, you know that we call catalysts are called enzymes in biology. So what I'm saying here for any garden variety catalyst also goes for enzymes. But I'm going to give you an example that's not from biology. And I will tell you that a catalyst lowers the activation energy of a reaction by providing what we call an alternate pathway okay? And I'm going to show what I mean there. So I'm going to talk about this reaction. This is the reaction that's the destruction of the ozone. So these are all in the gas phase. Ozone reacts with oxygen atoms to form oxygen, okay? And this is what we call the destruction of the ozone. And it happens in the stratosphere, way up there, okay? So this reaction, it turns out, this is catalyzed by chlorine atoms. And you might ask, where do these chlorine atoms come from? Does anybody know where they come from? Or some of them come from? Many of them? Anybody here what compound or what type of compounds promote the destruction of the ozone, and that's why we've changed certain chemicals that we use in certain situations? So, all right. Has anybody ever heard of CFCs? These are chlorofluorocarbons. So these are things in freons, in air conditioners, in propellants. And they contain chlorine, and these contribute to the Cl atoms that end up in the stratosphere, believe it or not, okay? And they catalyze this reaction. So here's the overall reaction, and it's pretty slow if it doesn't have a catalyst. So I'm just gonna write that down. It's slow without a catalyst. Although we still don't know how it happens, because this is just an overall reaction. But with the catalyst, which are the Cl atoms, this is the mechanism. Okay, so in the first step, the ozone reacts with the catalyst, Cl, to produce ClO plus O2. This is the slow step of the reaction. The catalyst almost always is in the slow step, because what good would it be to catalyze a fast step? It would, well, it might in the body, might be some reason for it, but what's slowing down the reaction is not the fast step, it's the slow steps. That's the one that needs the catalyst. Okay, so that would be step 1. In step 2, the ClO that was produced in the first step reacts with an oxygen atom, and this occurs much faster, to produce, again, Cl atoms plus oxygen. So you'll notice that Cl is used up and then it's regenerated. That is typical for a catalyst. So that means if you've got a lot of Cl atoms in the stratosphere, it doesn't just catalyze one of these reactions. It's not used up. It can catalyze the next one and the next one and the next one. So it's particularly destructive, right? So, so the catalyst is Cl. Cl is the catalyst. A catalyst is used. It's used in step 1, and then it's regenerated in step 2. Okay. You can also see that we have an intermediate. What is the intermediate here?
Oxygen?
Actually, if you look at the overall reaction, and thank you for trying, I really do appreciate it. The oxygen is actually a product of the reaction. When you're looking for an intermediate, what you have to do is you need to look for something that forms in one step and is used up in a later step. So a catalyst is used in one step and then forms in a later step, is reformed, is regenerated. An intermediate forms in one step and is used up in a later step. So that must be what here then? It's a ClO. This is the intermediate. So ClO is the intermediate because it forms in this step here and then it reacts away in the second step. So if you add these up, and you know, this is what I do when I add 2 reactions together. I line up the arrows. That way I know what's on the left and what's on the right. And just like with a math equation, you can cancel things. So I'm going to cancel, oops, I didn't mean to actually do that. I wanted to use the highlighter. Cancel the ClO. It's on both sides. It is generated here and then it reacts away here. The Cl reacts here and reacts away in this step, it goes away, and here it's produced again. So you can cancel those. So if you cancel those, you end up with O3 plus O goes to 2O2. And that is the overall reaction that I wrote up here. But it occurs as this in this mechanism here. So given what I just told you about the slow step determining the rate law, what is the rate law for this reaction? Rate equals what? What is the rate law for this reaction? So the rate law of a reaction equals the rate law for the slow step. Okay, So what is the rate law for the slow step? Remember, it's very easy to figure out the rate laws for an elementary step because they occur as written. So what type of reaction is this? What's going on here in the slow step? What do we have? The O3 is reacting with the Cl. They're colliding and forming an intermediate and O2. So what is the rate law for that step? What is the rate equal to for step 1?
Would it be KO3 and Cl?
That's right. K O3 Cl, because O3 and Cl are in that step. Okay. So, Chelsea, did you leave out the Cl because it was a catalyst? Yeah. Well, then you need to know now from now on that the catalyst can be part of the rate law. So here, this is the catalyst. Lots of times catalysts are in the rate law because where do you have a catalyst? You have a catalyst in the slow step, okay? And it's very intimately involved with the slow step. In fact, a slow step is a collision with the catalyst. So I guess I would say that catalysts indeed can end up in a rate law. So I can see why you left it out, but yeah, it wasn't right. And the other one is a square, so I don't know quite where you got that from, but I hope that you understand what the rate law is. So, okay, so here is a diagram for this reaction. Now, this is an exothermic reaction. You would have to be told that. You couldn't figure that out just by looking. Okay. So you'd have to be given that. And okay, so what this is showing is what the reaction profile looks like without the catalyst. So without the catalyst, remember that's if this reaction happens without a catalyst, right? There's nothing to decrease the activation energy or provide that alternate pathway. This is like another path of undergoing the reaction. So the activation energy is much higher without the catalyst. Okay. So this is the uncatalyzed pathway. Has a higher activation energy. So now you've got this, the activation energy has come down. It's come down from here. This would be the pre, and this is what it is after. This is the EA uncatalyzed, and this is the EA catalyzed. Okay. And what is this little valley in here? What do you think we should put in there? So you have your first step, activation energy, and then you have your intermediate here, your CLO intermediate, which then reacts away. This is EA2 in the second step, okay, which is a much faster step. Okay, so you could see again here, EA1 is greater than EA2. Step 1 is the slow step. Okay. So sometimes, people illustrate the effect of a catalyst different ways, might put a dotted line like that, but the real right way to do it here would be to put that little bump here, the 2 steps, because we know the first step has a higher activation energy than the second one. Okay, so the activation energy is a height of that bump from where you start to where you have to end up, the transition state. Then you have this intermediate here, and you only have to go a little higher to get over that next bump. And that means that the whole rate is determined by the rate of the slow step. Okay, so I'm going to show you some examples now. It's 3:15, so I have a few examples to show you. And then I'm going to give you one more diagram of an enzyme substrate reaction. Actually, I might just do that now because I don't want to run out of time. So let's talk about this, okay? So what this is another example of an enzyme. Oh, this is an enzyme catalyzed reaction. So what these are, you know, these spoke, these molecular models, I guess I should say. The black is representing carbon. The red, as always, represents oxygen. And the white is hydrogen. And this is showing a sucrose molecule, okay? And what this reaction is what we call the hydrolysis reaction of sucrose, a reaction with water, okay, to produce the two simple sugars, glucose and fructose. So basically, this is the bond here. This is the important bond. That's the bond that connects the glucose and the fructose. And you can see over here that that bond is broken. Okay. So this reaction is really the breaking of this bond. And the question is, you know, if it's catalyzed by an enzyme, which we call sucrase, then sort of how does this work? And I have to tell you, I took this picture from a book, and I love this picture because it's really a very sort of a, it's not giving you a whole lot of details, this picture, but it gives you the overall picture of how enzymes work to make reactions like this go faster. So if you just try to break this bond, that's a lot of kilojoules per mole to just go in there and break that bond. That's really, you've got to distort it. You've got to go through a very high energy transition state. So the question is, how does sucrase help? How does the enzyme, the catalyst, how does it provide a different pathway? How does it help? And so here's the picture. And I love this totally general picture because all this tan brownish stuff over here is representing the active site of the enzyme. And here is the sucrose, and it's showing the glucose, and so one of these is probably glucose, I don't know which is which, and fructose. And it's showing this bond here. But what happens is that this part of the glucose and the fructose interact with the enzyme by all of those forces that I've taught you about in the beginning of the semester. So these are intermolecular forces that attract the glucose and fructose to different bits of the substrate. And you know what these are. These are like oxygens that are delta negative, you know, and high. So this would be on the glucose, on the sucrose. So this is the substrate. Okay, so this would be on the substrate, and then this would be on the enzyme. Or maybe you have a nitrogen that's delta negative and a hydrogen that's delta plus. Or maybe you have a nitrogen that's delta plus and a hydrogen here delta negative, a hydrogen that's delta plus. So this is the substrate and the enzyme. That's what these interactions are here. And what they do is they kind of pull the molecule a little bit, stretching that bond. If this bond is stretched, it's weakened, it's not as strong. And that means it takes less energy to break the bond. because of, all of these attractive interactions. These are all attractions between the enzyme and the substrate. And these are intermolecular forces. So those intermolecular forces, in the sense, are providing, the release of energy from those attractions, weaken this bond and make this whole thing easier to break. And so that's an illustration of, how an enzyme, just with this cartoon, how you can now understand, because you know about intermolecular forces, that, this situation is stabilized by those nice intermolecular forces. And in doing so, it actually stretches that bond and makes it easier to break, so that the reaction happens more quickly. So it takes less energy to break that bond. The EA is lower and the reaction is faster. So that's a very nice cartoon picture of, I'm sure that when you take upper level biology and even chemistry courses, if you do such a thing, that you will, I know we teach 400 level courses where you actually are taught what these specific interactions are that allow an enzyme to function, to lower this energy so that this reaction can happen. So I think that's pretty cool. I hope that you agree. All right, so let's take a look at some of these examples. So here is an overall reaction. I should probably put that this is liquid. It doesn't really matter. So here, hydrogen bromide reacts with oxygen to form water and bromine, liquid bromine. I don't know what the name of that type of reaction is, but these are the steps in which that occur. This is the mechanism here. Okay, the steps of the mechanism. And it's a little on the complicated side. Like, take a look at this. So one of there's 4 HBRs here. One of them reacts with oxygen to produce this weird looking thing, HOOBr, which then reacts with another one of the HBr reactants to produce this other thing. Then this thing that's been produced here reacts with another 2 of these reactants to produce the products. So let's first of all, one thing I ask you to do a lot is to check that the overall reaction is the sum of the steps. So it would require us to add this up. Okay, but down here further, it says, if there are any intermediates, circle them. If there are any catalysts, put them in a box. So when we look for intermediates, what are we looking for? An intermediate is generated in one step and then reacts away in a later step. Okay, so give me an intermediate in this reaction.
HOOBr.
Definitely. It's generated and then it goes away. Okay. What's another one?
2HOBr.
Yeah, this actually has 2 intermediates, the same molecule, 2 of them, and then they react away. So these are circled in red. And I will cancel them, right? Because it's produced and then it goes away. And it's produced and then it goes away. Okay, so now let's look for a catalyst. Maybe you know there's no catalyst because I didn't ask you to find any here. There's no catalyst because what a catalyst is used in one step and regenerated in a later step. So let's look at this now. We have oxygen. Is that a catalyst? No, that's a reactant. You could see that it goes away completely. You don't get oxygen coming back here. So O2 is not a catalyst. because it's not there. Sorry, it's not regenerated. It's just gone at the end of the reaction. Okay. And actually, so we've already canceled the intermediate. So let's count the HBRs. Here's one, here's another one, then there's 3, 4. So there's 4 HBR on this side. There's 1 O2. Notice I line up these. That's the best way to do it. Gives you 2 H2O plus 2 Br2. So yes, this is the correct overall reaction. It does add up to the overall reaction. Okay, now here's the more interesting question. Given this information, what is the rate law for this reaction? So
Is it K, HBr, and O2?
yes, the rate law for the reaction, thank you, is the rate of the slow step. Here's the slow step. It's first order in each of these things. I don't know what that thing is there, but it's first order. So the slow step is first order in O2 and in HBr. So therefore, the rate law for the entire reaction, which is the rate of the slow step, is also that. So that is the rate law for this reaction.
I just have a question.
Yeah.
So if it was in second, would it be like the 2 HBr if that was in the slow reaction? Okay.
Wait, if it was the rate law, if it was the second step, it would be HOOBr times HBr. It'd be whatever's there. You
Okay.
only have one HOOBr there, so you would actually have that. And then if you were doing a really good job, you'd write that in terms of other things, but we're not getting that complicated here.
Okay.
So, okay, so we have this reaction. We have 3 steps. The slow step is step 1. And I'm telling you that this is an exothermic reaction. So if you were going to draw the reaction profile, what would it look like? So you would start, you say, okay, it's exothermic. Of course, you don't know these numbers of these activation energies. But the fact that the slow step is step 1 means that the biggest bump is the first bump. And then you'll have 2 smaller bumps on the way to products. So this is the activation energy for the first step. This little guy here, that's EA2. And then this little guy here is EA3. You have to start here from the middle, from that valley in between the two, which is where you have those intermediates. So that first valley would correspond to HOOBr. And the second one would be HOBr2, HOBr, I think, right? Yeah. Okay. And so this would be the reaction progress. That's what we say, the core, reaction progress. Sometimes it's called reaction coordinate. That's what it means, reaction progress, energy. This is the delta H over here. If we, delta H would be negative because it's an exothermic reaction. I didn't do such a good job on the, do a better job. So this has to really be the same. So this is the delta H here. Okay. There. This is the transition state. These other ones are also, but they don't count because they're lower. This is the one that's really got the big activation energy, the big bump to go over. All right. Okay. Let's talk about the iodine clock reaction, because that's the reaction that we did in lab. And you know, we found out that the reaction is first order in each of these two. Well, we found out that it's second order, first order in persulfate, and first order in iodide. That's what we did in lab last week. Okay, so the rate law for the above reaction is first order in S2O8 and first order in iodide. But this is the mechanism. It is a 4-step mechanism. Okay, so we are going to add up these steps and see if we get the right overall reaction. But what's easiest to do first is to see if there are any intermediates or catalysts. So there's a lot of stuff going on. I'm going to make it bigger because these negative signs are a little hard to see. So this has a negative, negative. These do not. This has 2 minus, 1 minus, 2 minus. Okay. So we're looking for a catalyst. A catalyst is used up and then regenerated. And we're looking for intermediates. These are generated and then used up. So let's look at intermediates. Give me some intermediates here. What's an intermediate?
SO4 minus.
Yes, SO4 with a single minus. So we're supposed to put a circle around the intermediates. What else?
Iodine.
Iodine, yeah. So it's produced in 2 places and then reacts away. Anything else?
Is I2 one?
Yeah. Okay, so what about on all the things we have left? So is anything used up, like is iodide, is it used up and then regenerated? Does it ever form on the right side? No. S2O8, does it ever form on the right side? Again, no. And in fact, when you add these up, which I should get a little more room to do. Ugh. I can cancel all the things, right? All these intermediates, because these 2 cancel with these 2. This cancels with that. This cancels with that. All intermediates cancel because they're generated and then react away. So that's how you know they're intermediate. So we end up with S2O8, 2 minus, plus 3 I minus goes to, here's the 2 things that are left over. SO4, 2 minus, 2 of them, plus I3 minus. And this is indeed, this is the overall reaction that you were given in lab. Okay, and you could see, by the way, that if you just looked at this reaction, you might think it was third order in iodide and first order in persulfate, because that's the way it's written here, but this reaction does not occur as written. Okay, we know that the rate law is K iodide times persulfate, right? The rate law is given right here, right? Okay, so given that this is the rate law, which step must be the slow step in this reaction?
Step 1.
step one, because look, here are the two reactants that you have here. Okay, they match. And so this must be the slow step, and all the other steps are faster. So we know that step one must be the slow step. And the reason is because its reactants match those in the rate law. And the slow steps rate law is the rate law for the overall reaction. Okay. All right. Does anyone have a question about that? I know it'll take a little studying. I have a final example here for you. And I'd like you to just think about it for a few minutes. I don't want to just write the answers. I want you to take a look at it. I don't know if you have it in front of you. I'll just put it like that so you can see the whole thing. Actually, I did put this on, I did email this to you, and there's more to it. I don't know if you could read it if I make it this small.
You can.
So I'll just put the whole thing on here. Because I'd like you to be able to do this type of problem. I'm just going to sort of give you a few minutes to look at it. Maybe 5 minutes. And if anyone wants to ask me anything, I'm here.
So would the OI negative cancel out?
Sorry, I didn't quite get that.
Would the OI negative cancel out?
Yes, it would. So what does that make OI negative? Is it an intermediate or is it a catalyst?
Intermediate?
Yes. All right, I didn't wait 5 minutes, but how's everybody doing with this? Any questions?
I'm still not entirely sure like what a catalyst is. It like reappears.
Yeah, catalysts are never used up. Catalysts help the reaction along, but they don't get consumed by the reaction because they're not reactants. They don't go away and form something else. They get regenerated by the end of the, so if you have like an enzyme substrate reaction and the substrate, like the sucrose molecule sitting in that enzyme, at the end of the reaction, the substrate goes away and the enzyme can take another substrate. So what you need to do is look for something that that gets used up, but then comes back later. And what is that in this reaction?
H2O2.
H2O2. You're saying that the H2O2 gets used up and then comes back, but there is no H2O2 on this side, right?
Yeah.
You know, you can add this up and you could see that this cancels and you could see that this cancels and you could see that this is the overall reaction. All right. The catalyst isn't there because the catalyst is used up and then regenerated, so it's canceled. This iodide is the catalyst. Right? This is the intermediate. Okay, so catalysts and intermediates cancel out. If you added this up and you said, oh, I have 2 H2O2 here, that must be a reactant because it's not a catalyst or an intermediate because it's there at the end. You know, it's in the overall reaction. These are products, right? Products aren't there at the beginning, they're there at the end. Reactants are there at the beginning and not there at the end. But intermediates, they're sort of invisible in the background, and same with the catalyst. It's used and regenerated. So I guess it's visible at the beginning and at the end, actually. So anyway, so what is the overall reaction? It's just what I've written here. This is the decomposition of hydrogen peroxide, okay? So can you answer now this question? Well, this one we just answered. What is the rate law is the question. What is rate equal to?
H2O2 and O2.
No. O2 is a product.
So just the H2O2.
No. Anybody else? You have to look at the slow step, Morgan. And you see that there are two things in the slow step.
The I.
You have to include the I. So oftentimes, so you can see from this example, as it says here, that the concentration of the catalyst may well end up in the rate law. And that's because the catalyst is really intimately involved with the slow step. So it's not unusual at all for it to end up in the rate law. Supposing I gave you this overall reaction, this is D. If you were given the overall reaction and the rate law, how could you tell that the overall reaction does not occur as written? So that's the question. How can you tell that the overall reaction does not occur as written? That is, it does not involve a collision of two peroxide. That's what that H2O2 is. Supposing this reaction, so if this reaction, so this is speaking to this question, if this reaction occurred as written, what would the rate law be? So if it actually happened this way, what would the rate law be?
It would only have the H2O2.
To what power?
2.
Yep. Because there's two of them colliding in this reaction. Okay. So that's the answer to that question. All right. Good. I have to post the lab handout. I'm going to do that after class. Yes, I seem to post them later and later because I'm working on them up into the minute. And anyway, we have a test later this week. I'm going to be giving it out on Thursday. So, you know, if you have your questions, get them answered. I'm going to have some extra office hours like I did last time. So think about when you want to have that happen, those office hours, and advocate for yourself. You want me to have some office hour on Saturday or Sunday or Friday or Thursday? Those are my days. Okay. The test is going to be due like a week after I give it out. And you have to time yourself. I mean, you have to, don't leave it to the last minute. You know, you want to work on it like on the weekend. You know, if you don't work on the weekend, or if you do, then you want to make sure you carve out some time for it. It doesn't just take an hour. It's going to take you a few hours for sure. So, but the thing about this, doing a test like this, is you don't study in advance necessarily. So, you know, somebody wrote to me that the test took 5 hours. And I have to say that, I mean, under normal circumstances, if you were going to have a chemistry test, how many hours would you study for that test? You might study 6 hours, you know, but in this case, you study when you get the quiz. You study in order to figure out the answers to the quiz. So it's almost like study time is part of the doing time, and you don't have to waste your time studying everything. You only have to study things that are asked. I think what I might do this time is actually help you find things in the notes. I might actually write an index, but I haven't decided quite yet. I'm curious. I'm on the fence about that, but I might do that so that you can know where to look in the notes for the questions on the test. Anyway, that's what I'm thinking about. But yes, okay. All right. So if anyone wants to talk to me, I'll be here for a while. So just hang around after class. I think I'm going to stop the recording though right now.
Professor, I have a